I'd now like to talk about heat diagrams or heating curves. Now, a heat curve or a heating diagram tells us the energy changes that occur as we heat up a substance from one temperature to another temperature. And in some cases, we are also going to take into account phase changes as well. And with water, we're going to go from a solid to a liquid to a gas, and all of that is going to be observed on the heating curve. Right, in order to do this, we need certain pieces of information. We need the heat capacities of each of the phases. So we need the heat capacity of the ice, the heat capacity of the water, and the heat capacity of steam. We also need the heat of fusion and the heat of vaporization, and these are going to tell us the energies required to actually melt or vaporize the substance. So let's talk about what's going on the heating curve. So we're starting out here at -5 degrees, and we're going up to 0, and at this point all we're doing is we're taking the solid, because we know that below 0 degrees ice will be a solid, so water will be a solid, and we're going to go from -5 to 0, and all we're doing is putting energy in order to take the ice from -5 to 0 degrees, and that takes 392 joules. Then at 0 degrees what we're doing is we're going to take the solid ice and we're going to melt it, and we're going to turn it into a liquid. What I really want you to see here is that during that time the temperature does not change. So not until all of the ice has actually turned into water does the temperature start rising again. So once every last bit of ice has turned into water, then we can start heating it again, and the energy required to heat it from 0 to 100 degrees can then be calculated. Then at 100 degrees what's going to happen is that the water is going to turn into steam, and again during that time the temperature will not change until all the water has turned into steam, and then at that point we can start heating the steam, and we're going to put a certain amount of energy to change the change the temperature of the steam from 100 degrees to 110 degrees. Alright, so let's look at some of the math involved here and see if we can figure out what's going on with some of these question marks. Alright, so we'll start off with the first one with the 392. I'll show you how we get that. Alright, so we're going to be looking at a change in temperature here from -5 to 0. So I think it's fairly clear that we're going to have to use the Q equals MC delta T formula. And the mass here we're told it's 18.02 grams. Give me a second while it catches up with me. And what we're going to use here for C is, because we're dealing with solid, we're going to use the heat capacity of the ice, which is 2.087 joules per gram per degree Celsius. And the delta T here, or change in temperature, is going to be from -5 to 0, which is going to be 5 degrees. So we're interested just in the, and I'm going to, just to make it a little bit easier with the significant figures, I'll just make it 5.000 degrees Celsius. We really can't tell what sig figs are based on what's going on with the temperature, but we'll make that assumption. Anyway, all of that's going to come out to be 392.0 joules if I use that. Alright, so that's going to be the amount of energy that needs to be put in to take the ice from -5 to 0 degrees. And notice that this is a positive value because we're looking at a change in temperature here. Alright, so next we want to look at this business here. We want to see what energy needs to be put in to take the water from a solid form to a liquid form. Now in order to do that, what we're going to do is we're going to take Q is going to equal the delta H of fusion Now, fusion is the process of freezing actually, but it's going to be the same going from melting from solid to liquid as it is from liquid to solid. So the delta H of fusion is going to be identical in each instance. So it doesn't really matter if we're going from liquid to solid or solid to liquid. So delta H of fusion is what we'll use there, and we're going to multiply it by the moles of substance. And the delta H of fusion here is 6.01 kilojoules per mole. And that's times, and we've got 18.02 grams, so we need to convert that into moles. And it just so turns out that 1 mole is conveniently 18.02 grams, because we're talking about water here. And that's going to give us 6.01 kilojoules per mole. Now, one thing I'd like to do is get a total on the amount of energy it's going to take to go from -5 to 110 degrees. In order to do that, I will want to be comparing apples to apples. So I've got joules over here in my first one. I actually want to convert this into joules as well. And I will do so by multiplying by 1000 joules over 1 kilojoule. And when I do that, I'm going to come out to be 6010 joules. Alright, so that's it. That's what we're getting on the first two. Right, let's see how we might get these other ones here. So I'm just going to delete this. Give it some room. Now what we're looking at is to calculate the energy required to get from here, which is liquid at 0 degrees, to liquid at 100 degrees. And what we're going to do there is use the Q equals mc delta T again. Again, the mass of water is still the same. You'll notice that regardless of the state it's in, it's still going to have the same mass. Now we're going to use the heat capacity of the water, 4.180 joules per degree, joules per gram per degree Celsius. And we're looking at the difference in temperature, which is going to be from 0 to 100, which is going to be 100, so 100.0 degrees. And when we calculate that out, it's going to come out to be 7,532 joules. Alright, so that's going to be the amount of energy it takes to go from 0 to 100 degrees just for liquid water. And again, we used the heat capacity of water to achieve that. Excuse me. Next, we're going to look at the energy required to take the water and turn it into steam. And what we're going to use there again is the delta H of, in this case, vaporization this time. This will be the energy required to take the liquid into steam. And again, it's times the moles. Now, I won't do the mole calculation this time. We already did that. We already figured out it's going to be 1 mole. But I will do the conversion from kilojoules to joules as well. So we're looking at 2.26 kilojoules per mole times 1 mole times 1000 joules over 1 kilojoule. And that's going to be 2260 joules. Alright, so that's the amount of energy it takes to turn that liquid water into steam. Alright, now we have to look at how much energy it's going to take to turn that steam from 100 degrees to turn it into 110 degrees. And again, we're going to use the Q equals mc delta T for that. And the mass is still 18.02 grams. The C is going to be the heat capacity of the steam. Joules per gram per degree Celsius. Notice how I'm always using my units so that I'm making sure that everything ends up with what I should get. And you see in every instance everything's cancelled to give me what I wanted. And the change in temperature here, we're going from 100 to 110, so we're looking at 10.00 degrees Celsius. And all of that is going to come out to be 358.0. And that's going to be joules. Just to demonstrate, you can see how this cancels. You've got degrees Celsius, you've got grams. So you're never in doubt about which units to use or which quantities are going to give you the values you want. So if we were to go ahead now and add up all those values we calculated going from -5 to 110 degrees, it's going to come out to be 16, 5, 552 joules, and that would be the total energy required to cause water to go from -5 up to 110 degrees. It includes heating the different phases and the phase changes themselves, the energy that they cost.